Hi everyone, so right now we are entering a new section which is on chapter 1 section 3. So chapter 1 section 3 is on motion of charges in uniform electric field. Okay, motion of charges in uniform electric field. Okay, but before we really talk about how charges move in the uniform electric field, probably we should give some time to study, to have a clear understanding on uniform electric field. Okay, we need to have an idea what is uniform electric field first. So we are going to start today's topic by talking about uniform electric field first. I know we have learned about electric field, but right now we are going to talk about uniform electric field. Okay, so the word uniform here means it's the same. So if we are talking about electric field, what does it mean by when they are the same? It means by this electric field, right, all across the region, you see that the electric field has a constant magnitude and a constant direction. It means that no matter where you look at in that region, you'll find the electric field at any position in that region to be having the same electric field strength, the magnitude, and same direction as well. Okay, so then what you can say is you can say that the magnitude and direction of electric field is a constant across the region. Okay, so a region is a certain space that you define, and in that space, you'll find that everywhere in that space, the electric field is pointing in the same direction and it has the same strength. So that's the meaning of uniform electric field. Okay, so we're going to start by discussing how do we actually make this kind of field happen? How do you make an electric field that is uniform across the region? We know that if we put a point charge, there will be an electric field around the point charge. That is what we have learned in the previous two sections. We know that the electric field goes by kq over r squared if you are talking about a single point charge. So it means by if you're going further away from the point charge, the electric field gets weaker and weaker. So just by reading the statement here, you know that this is not a uniform electric field because just like I mentioned, it gets weaker and weaker as you go away and away from the point charge. So you know that the electric field produced by a point charge here is not the uniform electric field. So right now it's actually important for us to actually investigate what kind of setup will produce a uniform electric field. Okay, so title for here is how to produce a uniform electric field. Okay, so to produce a uniform electric field, you actually need two requirements to be fulfilled. So I'm going to talk about these two requirements. Okay, so the first requirement that you need to do is you need to ensure that you have a pair of conducting plates. Okay, pair of parallel conducting plates. Okay, and then you need to make sure that for this pair of conducting plates, you need to ensure that these two plates here are actually oppositely charged. So these are the two important criteria that you need to achieve in order to have a uniform electric field. Okay, so what does it mean? Let's say today you have let's say this region here, this particular region. and you want this region here to have a uniform electric field inside it. So you want this region to have a uniform electric field. Means by no matter where you look at inside this orange box, you find that the electric field at anywhere inside this orange box will have the same magnitude of electric field and same direction of electric field. So if you want to make that happen, what you should do is you should have a pair of conducting plates. So the pair of conducting plates, you have to sandwich this region in between it. So an example of it is to place the plate, one of it on top, then one of it below. So this is a setup that you need here. You need a pair of plates. So that's why there's one plate and two plate, and they are parallel. And these two plates supposed to be made of conducting material. So conducting material can be like metal, copper, gold, silver, any kind of material that conducts electricity well. So you have a pair of plates and they're conducting, and you need to arrange them in parallel arrangement. So they are now in parallel arrangement and they are sandwiching this region over here. So the region being sandwiched over here, inside this region here, you'll be able to see uniform electric field produced by these two plates. But these two plates here have to follow the second requirement as well. Means that they should be oppositely charged. So if you want it to be oppositely charged, that means you have to somehow make one plate to be, let's say I'm going to make this plate to be positive plate, whereas I'm going to make this plate to be negative plate. Okay, so this is the idea of oppositely charged. So it can be some kind of a power supply to make this happen, or it can be some kind of battery, or some kind, any kind of generator in order to produce this positive terminal and this negative terminal. So if you have positive terminal over here, that means this plate over here is going to be positively charged. And this plate down here will be negatively charged. That is the we are following the terminal that we indicate here. Okay, if you connect a battery with the positive terminal over here, negative terminal over here, then you create a positive plate over here and a negative plate over here. Same like any power supply, you connect the positive terminal, then this plate will be positive. You connect the negative terminal, this will be negative. If you connect the negative terminal over here, then you create a negative plate over here. If you connect the positive terminal over here, you create a positive plate over here. But the most important thing is they must be oppositely charged. Okay, you can have two positive plates, you can have two negative plates. You must have one positive plate, one negative plate. Okay, so if you refer to the idea of charges, which is probably in section 1, you learn that if something is positively charged, you can know that the idea of how you can able to reach a positively charged, how is an object able to be positively charged is that the number of protons is greater than the number of electrons. Okay, whereas on the other side, which is negative plate, why do you have negative plate? Is because the number of protons is less than the number of electrons. Okay, so just by understanding this, you can see that in order to be able to create this positive plate and negative plate, you somehow have to make this plate to have more electrons. You need to make this plate to have less electrons. You know that electrons is the only charged particles that can move, right? I mean subatomic particles that can move. Protons, they are stuck inside a nucleus, they cannot really move. So only thing that can move right here is the electrons. Okay, especially for metal, you know that they are free ions. I mean, it's this electron C model. You know that they are free to move. They are delocalized electrons. So if you want here to have more electrons, here to have less electrons, what you need to do, you need to ensure that there are electrons going from this plate to this plate. Okay, so there will be electrons moving here. Okay, maybe this way of writing is a bit confusing. Let's use an arrow like this. I will be saying that there will be some kind of charge or electron flowing from the positive plate to the negative plate, and that will result in the plate over here to be negatively charged, whereas this plate will be positively charged. Of course, you'll be thinking, is it okay if I flip the situation? Let's say I put here to be the negative plate, here to be the positive plate. Okay, no problem. You just need to bring your electron from the lower plate here to the upper plate. Then you are able to make the upper plate to be negatively charged, the bottom plate to be positively charged. Okay, so if you fulfill these two conditions here, you are able to make a uniform electric field in between that two plates over here. Okay, so right now we are going to study about three different aspects of this setup over here. Okay, the first aspect that we are going to study is the magnitude of the electric field. The second aspect that we are going to study is the direction of the electric field. The last thing that we're going to do, which is actually not really strictly in the syllabus, but I think it's good for you to have an understanding, is the electric field lines. How does electric field lines looks like? Okay, so first of all, we talk about the magnitude. Okay, last time we learned about the magnitude of electric field. You can use equations like E is equals to K Q over R square. You learned about this produce equation, right? And then you also learned about the interact equation, where the interact equation is E is equals to F over Q. Okay, so here I would like to remind all of you that when we talk about this particular equation is actually derived by taking this equation and you substitute F with Coulomb's law. Okay, if you put in Coulomb's law, KQQ over R square inside this F over here, the small q cross out, then you're able to get this equation over here. So what I'm trying to say is that this equation here comes from F is equals to KQQ over R square. But if it comes from KQQ over R square, you know that KQQ over R square is referring to 2-point charge at a distance apart. You have big Q, small q at a distance apart. You want to find the electric force between them, you use KQQ over R square. But in this case, I would like to highlight once again, this is not 2-point charges acting. You don't have 1-point, 2-point charges acting with each other. Right now, the situation is a uniform electric field. So that means that this equation can no longer be used. Okay, can no longer be used because it's not produced by point charge. Okay, but this equation you can still use it. Okay, this equation still can use it, just that this equation you can say come from F is equals to KQQ over R square. Okay, so because it comes from Coulomb's law, then therefore you cannot apply it because Coulomb's law is applicable to 2-point charges only. Okay, so I hope this part is clear. See, okay, so we need a new equation. So the new equation for us to study the magnitude of electric field. Okay, I'm not going to do a derivation. The derivation is a bit long for this one. But I'm going to let you know that there's a new equation for the electric field magnitude, which is E is equals to delta V over D. Okay, delta V is something you might be familiar with. You've learned about it in the previous section. This is actually potential difference. Okay, potential difference, but usually is between two plates, usually. Okay, so usually take the V high minus the V low. Okay, because we talk about between, right? So there's no sense of direction, but usually we just take V high minus V low. So the higher electric potential plate, take the electric potential minus the lower electric potential plate, it's electric potential. So if you look at this situation here, we know that positive plate, they have a positive electric potential, whereas the negative plate, they have a lower electric potential. So usually take the positive plate's electric potential minus the negative plate's electric potential. Okay, so this D over here will be representing the distance between plates. Okay, so if you find the distance between these two plates over here, which is from here to here, if you make the measurement, this distance over here, you can substitute it inside this D. And by using these two values only, you're able to determine the electric field that is produced in between these two plates. How strong is the electric field can be determined by this equation over here. Okay, just want to let you know that even though right here is potential difference between the two plates, right? It can be used in situation where we don't talk about the two plates actually. You can use it because you know that everywhere here, everywhere in this region over here, the electric field is the same, right? It's constant. So everywhere in this region, if you find the electric field strength, you get the same E. So that means by if you don't take this V minus this V, if you don't take V high minus V low, if you choose to take V middle, higher middle, or V higher middle minus V lower middle, and divide by the distance between V higher middle and V lower middle, you can also find the electric field strength as well. Okay, it's up to you. You can, I'm just rough sketching only. You can take the distance between here and here. Then this distance here, it's D, right? So this point will be V high. This point will be V low. Okay, but today you can choose to do it differently as well. You can choose to take here instead. Let's say if you take between here and here, then the distance will be D over here. Then in this case, this one will be V high. This one will be V low. Okay, so what I'm trying to say is it doesn't necessarily have to be the electric plate itself. It doesn't necessarily have to be the upper plate minus the lowest plate, and the positive plate minus the negative plate electric potential divided by the distance between the plate. Because the value everywhere here, the E is the same. You can actually take any 2 points, find their distance, distance between them, then you find the electric potential, then you can calculate using this equation as well. Okay, so it's not really necessarily strictly used for in between plates. Any region in between the plates also usable this equation. Okay, so that's the equation for magnitude of electric field. It's not really derived, but I hope it helps you to see the idea. Okay, but from this equation, I'd like to announce to you something interesting in which you might already see that this one, the unit is V, whereas distance between plate, the unit is M. So that means by you have a new unit for electric field. The new unit for electric field is volt per meter. Of course, if you choose to rewrite it as Newton per Coulomb, it's still acceptable as well. So you have two units for electric field, either volt per meter or Newton per Coulomb. Both are acceptable. Okay, you just think about it. This is volt, this is meter, so volt per meter. Okay, so this is the magnitude of electric field. Now we talk about the direction of electric field. How do we determine the direction of the electric field? Well, it actually stems from what we have learned from previous section. Okay, we know that the electric field is produced. This time it's not produced by the parallel plate. This time it's not produced by the point charges. This time it's produced by parallel plates, right? So if it's produced by parallel plates, so what happened right now is you will point away. Okay, produce, right? We're talking about produce over here, so it's point away and point towards. Okay, so point away, usually we say point away from a positive point charge that produce the electric field, right? This time is still the same. It's pointing away from the positive, not point charge, positive plate. Okay, so we are pointing away from positive plate, and we know that we are pointing towards a negative charge that produces the electric field, right? So this time we are pointing towards the negative plate. Okay, we are pointing towards the negative plate. Okay, so one important thing that I should jot down is as well is that the electric field is always perpendicular to the plates. Okay, so to give you an example, let's say this is my parallel plate. And my parallel plate is connected to, let's say, a battery. Okay, if I connected it to a battery in this way, maybe let's twisting a little bit. Let's connect it to a battery in the opposite way. So if we connect it like this, then right now, what happens is here it will be the positive plate, whereas the other side, the upper plate, will be the negative plate. So for this kind of situation, let's say you want to find the electric potential at 3 different points. Let's say you want to find electric potential at X. Let's say you want to find electric potential at electric field, sorry. Let's say you want to find the electric field at Y. You want to find the electric field at, let's say, Z. Okay, everywhere in this region, as I mentioned just now, you have same magnitude and same direction. So you should expect the X, Y, and Z, their electric field to be exactly the same. So we learned that the electric field, the direction is pointing away from the positive plate. So if you want to point away from the positive plate, you should be pointing towards upwards, right? You should be pointing upwards. You must be pointing towards the negative plate. So upward is definitely pointing towards the negative plate. And E is perpendicular to the plate. So if our plate is horizontal, we know that our electric field should be vertical. So just by knowing these three statements, we are able to say that the electric field should probably be pointing somewhere like this. Okay, this is the electric field at X. Then Y should be the same length because same strength, same direction because then same direction of arrow. Okay, this should be EY. Okay, EZ should also have the same arrow length because that's the same magnitude. This is EZ, same direction pointing upwards. Okay, so just by knowing these 3 points pointing away from a positive plate, pointing towards the negative plate, and perpendicular to the plates, you are able to determine the direction of the electric field. So now you have know how to determine the direction of the magnitude of the electric field. You have learned how to determine the direction of the electric field. And now the last thing to learn about right now is the electric field lines. Okay, electric field lines. What is electric field lines? Probably deserve a bit of explanation. So it's basically lines used to indicate the magnitude and direction of electric field. Okay, so you need to know about magnitude and direction. Okay, so what do we need to know? Okay, so if you're talking about electric field lines, there'll be a lot of lines in that region. Okay, so those lines will tell you at a certain point how strong is the electric field and what is the direction of the electric field. Okay, by just looking at the electric field lines, you're able to know which region you have stronger or weaker electric field, and at the same time, you're able to determine the direction of electric field. So how does it work? Okay, for magnitude, right, the electric field line will tell you how strong or how weak the electric field by looking at the density of the line. Okay, so you can say the denser the electric field line, the stronger the electric field. The magnitude of electric field. Okay, so this is the idea. Okay, next, for direction, how does it tell you the direction of electric field? Well, direction of electric field is tangential to the electric field lines at a specific point. Okay, so let me illustrate to you the idea first. Okay, I'm going to use an example of what we have learned in secondary school actually. Okay, so let's do it in brown maybe. Okay, we are going to recall what we have learned from school. Recall from, I think this is form 5 maybe. If you have a positive charge, okay, the electric field lines should look something like this. You will have lines pointing out of the positive charge. Okay, it's something that you have learned before in school, but it's actually not in metric syllabus. Okay, so you know that the line will be pointing out like this. Okay, this is the electric field line for a positive charge. Okay, so what can we say from this particular diagram is we can see that comparing, let's do it in green. If we compare between this region You compare this region. This one is denser. This one is denser. Whereas this one is less dense. So that means by here you have a stronger electric field. Whereas here you have a weaker electric field. Okay, let me zoom in a little so that you can see things clearly. Okay, this is your diagram over here. So as you can see in this particular box, over here, you can see that you can fit in about 3 lines inside this box over here. There's 1 electric field line, 2 electric field line, and 3 electric field lines squeezed within this box. But if you move to somewhere further away from the point charge, you can see that the same size box will probably fit only 1 single line in it. So therefore, you can see that the electric field lines over here is more closely packed, or you can see the words, the electric field lines are denser over here. So if you have a denser electric field lines, the denser the electric field lines, the stronger the magnitude of electric field. So that means by here you will see a stronger electric field strength over here. Okay. On the other hand, if this place over here, you can see that the electric field lines are more further apart from each other. They are more loosely packed. So in this case, you can say this one is less dense. So because it's less dense, then the electric field over here will be bigger. Not less dense, less dense. Okay, less dense. So that's why the electric field will be bigger. Okay, I'm giving you an example from school so that I can relate it to what I want to discuss later. Okay, so the green one will be the magnitude. Okay, right now let's talk about direction. We say the direction of electric field is tangential to the electric field line at a specific point. So let's say today I want to determine the electric field line. I want to determine electric field at this point. I want to determine the electric field at this point. I want to determine the electric field at this point. Okay, so how do I determine the electric field line at this point? How do I determine the electric field, the direction of electric field at this point? The direction of electric field at this point is tangential to the electric field line. So the tangential to the electric field line is in this particular orientation. So that means that the electric field will be tangential to this line at this point. So how to be tangential to the electric field line at this point is to point upwards. So that means by your electric field at this point is pointing this direction. Okay, so applying the same idea over here, if you want to find the electric field, the direction of the electric field at this point, you want to find the tangent line to this electric field line. You want to find the tangent to this electric field line at this point. So how do you be tangent to this line at this point? Is to point in the same direction as it. So you know that your electric field pointing in this direction. So using the same idea, you find that the electric field is also pointing in this direction. So if you find tangential direction to any electric field line at a certain point, you're able to know that point electric field, what's the direction of the electric field at that point. Okay, so I'm just demonstrating to you how to understand the electric field line. By looking at the density, you know the magnitude. By looking at the direction of those lines and find a tangential line to it, you're able to determine the direction. Okay, so why do I talk about all these things? Why do I go circle a big round? It's because now I want to talk about uniform electric field. Okay, if I talk about uniform electric field, when I say it's uniform magnitude, what do I mean? Is that I will have uniform density of electric field lines. Okay, because that's what mentions up there, right? Okay, the denser the field line, the stronger the magnetic field, the stronger the magnitude of electric field. So if my magnitude of electric field is the same all over the region, then the density of the electric field line must be the same all over the region. Okay, so I don't have places which are more closely packed. I don't have places which are more loosely packed. Okay, everywhere you see the distance, the distance between the electric field lines are the same. Okay, there's no places where you find the electric field line to be further apart. There's no place that are closely packed. They are all having the same density of electric field lines. Okay, how about direction? The direction is talking about tangential to the electric field line, right? We usually follow the direction of the electric field line tangential to it. So we know that the electric field is perpendicular to the plate. Therefore, we can say that the electric field line should also be perpendicular to the plates. Okay, this is what we can know. Because you want to be tangential to the line, then you can find the direction of electric field, right? So if your electric field line is like this, then your electric field also like this lah. If your electric field line is like this, then your electric field also point in that direction. So if you know that for this particular situation, you know that electric field is pointing upward, then your electric field line should also be aligned with this electric field. So it should be a vertical line. Okay, so knowing all these things, over here, you can finalize the electric field lines. And can I make it neater? So knowing all these things, I can probably make a conclusion. My electric field lines for a uniform electric field let's say if up there is positive plate, if down there is negative plate, then my electric field line should look something like this. Okay, why do my electric field lines look like this? Because I say that the density of the line should be the same across the whole region. So you can say no matter where you see the electric field lines to be about the same distance apart. There's no places where you see the lines to be more closely packed. There's no region that you see the line to be more loosely packed. Everywhere it's the same level of density across the whole region. So that solves the magnitude problem. But why do I align my lines vertically? Is because if I align my lines vertically, my electric field, no matter what, will be tangential to this line. So tangential to this line means by you follow along this direction in this particular case. So in this case, it can point upwards or point downwards. But if I indicate my direction of my electric field lines to be pointing downwards, then this will be the electric field. Okay, this is the electric field lines. Okay, so if you find anywhere, let's say this point, or that point, or this point, you find that the electric field must be tangential. So here the electric field will be pointing this direction. Here the electric field will be pointing this direction. Here the electric field will be pointing this direction. So no problem with this particular setup. Okay. So this will be how the electric field lines looks like for uniform electric field. Okay, so if you want to describe this electric field lines, then we can say that these electric field lines, you can say that they are equally spaced. Okay, because they have same magnitude, then you can say that it's away from positive plate and it's towards the negative plate. Okay, so this is what you can think regarding the electric field lines produced by these parallel plates. Okay, so to sort of wrap it up, okay, make it neater. Okay, so to sort of wrap it up, we learned about uniform electric field. How do you want to produce it? You need to fulfill two requirements where you have a pair of conducting plates, and that a pair of conducting plates must be arranged in a parallel arrangement. So if you have opposite charge in between these two plates, one plate put it positively charged, one plate put it negatively charged, you are able to produce a uniform electric field in between these two plates. Okay, so the how usually we do that is we connect it to a power supply or a battery, in which you shift electrons from one plate to the other plate, making one plate more positively charged and another plate more negatively charged. Okay, you'll learn more about this in chapter 2 actually, but I'm going to leave it here. Okay, so regarding this uniform electric field, we learned about the magnitude, the direction, and the electric field lines. The magnitude of electric field, you know that this equation is not usable anymore. You have new equation, which you take the potential difference V high minus V low, divide by the distance between V high and V low. Then from there, you are able to get the electric field magnitude, but you know that the magnitude of electric field, we have two different units, both also usable, volt per meter or Newton per coulomb. Okay, next for the direction of electric field, you know that the direction should always point away from a positive plate and towards a negative plate. So in this case, positive plate is below, a negative plate is above, so it points from down to up, and it must be perpendicular to the plate. So if the plate is horizontal, the electric field will be vertical. So vice versa, if the plate is vertical, then the electric field will be horizontal. So that's magnitude and direction. For the electric field lines, you take information from the definition where the magnitude and the direction is constant. So magnitude is constant means by the density of the electric field line should be constant. So you know that your electric field line should be equally spaced. The direction of the electric field must always be perpendicular to the plate. So the electric field line must also be perpendicular to the plate. So this is how your electric field line should look like, in which they are equally spaced and they are pointing away from the positive plate towards the negative plate. So these are the important information regarding uniform electric field, and in the next video we'll study what will happen if you send charges into this uniform electric field. How will it move, how will it deviate from its initial path, and how to study the motion of it using some concepts that we have learned from last semester when we talk about kinematics of linear motion.